Okay, so this is part 2, you guys, of yesterday's lesson, which has to do with graphs, paths, and circuits. And I have a few definitions to talk about. This will go pretty quickly, though. A degree of a vertex is the number of edges at that vertex. Okay, one thing you guys need to know is that a loop is considered 2 degrees because it goes out of the vertex and back into the vertex. So write that down somewhere. Okay. An even vertex is a vertex with even number of edges attached to it. So guess what an odd vertex would be? So it's a vertex with odd number of edges attached. Okay, adjacent vertices. These are vertices that have at least one edge connecting them. I want to look at some of these vertices that we have right here. Let's look specifically at vertex A. Okay. Tell me, what is the degree of vertex A? 2, because there's 2 edges coming from it. Okay. And is it an even or an odd? Even. Yep, it's even. Okay. Now, I want to know what are some adjacent vertices to it. So, yep, it'd be U would be one of them, and H would be another. Would G be considered one? No. It doesn't have a direct line to G, right? How about L? No. L is proximately next to A, but it's not adjacent because there is not an edge leading to L. Okay? So the other one we can look at, let's look at vertex U. No? Oh, okay, sir. So vertex U is a degree of what? Actually, more than that. How many degrees is a loop? It's 2. So you can basically put 2 marks on it. So I counted 5 edges coming out of U. So that would be 5th degree. Okay. And it is considered an even or an odd? Odd. And the adjacent vertices to that be A, what else? S, and G. Okay? So let's look at 2 more definitions. Path and a circuit. A path is a sequence of adjacent vertices and edges connecting them. Okay? So one of the things you need to know when thinking about a path, an edge can only be part of the path once. You cannot use the same edge more than one time. I like to think of this as 2 things. Well, one thing in the book is they talked about a mailman and he's walking from house to house to deliver mail, okay? He's going to want to go the shortest route because he wants to make his life easier. He's carrying weight in his bag, and he doesn't want to have to go down a path he's already been. So when he's going down the street, he's typically going to go down one side of the street and come back up the other side. He's not going to zigzag across the street going back and forth, typically, okay? Because that's more steps he has to make then. And I also like to think of it as Halloween. Because for me, at Halloween, I wanted to get to every house as I could so I could get more loot, okay? Candy's important at Halloween, and you want to make sure that you take the least amount of steps because you wanted to go as many houses as you can. So whenever I thought about my routes for Halloween as a kid, I literally would sit and think this out, you guys. I would plan on going down one side of the street, come back, and I'd plan all of my blocks accordingly to make sure that I had the smallest amount of steps and the maximum amount of houses I could go to without using the same path twice. Okay? So that would be an example. A circuit. A circuit is a special kind of path that begins and ends at the same vertex. Okay? So one thing you should know that paths and circuits do not have to include every vertex or edge in the graph. So not everything has to be used. Okay? In front of you now you have a graph, and we want to find two paths from U to H. Okay? So U going from U to where? What's the next point you can go to? G to H, right? That's one path. What's another path? U, A, H, and then I heard U, S, H. Okay? Those are pretty easy, straightforward paths, or you could take a more winding path, couldn't you? You could go U to U in that loop, okay? S to L to H. U, U, S, L, H. Okay? So those are some different examples of paths, and notice that we're not using the same edge twice, ever. Find two circuits beginning at U. So two circuits beginning at U. The easiest one there is what? U to U, using the loop. What's another circuit? U, G, H, A, and then U. That's a circuit. What's another one? U, S, H, G, U. I can also see another one like U, S, H, A, U. Right? That could be another one. Okay. So those are various circuits and paths that you can have. Now we're going to switch gears a little bit, talking about connectedness. A graph is said to be connected if for any two of its vertices there's at least one path connecting them. Okay? So a graph would be connected if all of its vertices have an edge of some kind. If you have a point floating off by itself, it's not connected. Or if you have what looks like two islands, it's not connected. So an example of this is if I have the following graph. Here's all my vertices. And you notice that every single vertex has an edge attached to it in some way. You might have more than one edge even. Okay, so essential characteristic of this, every vertex has an edge attached. Okay. So if it's not connected, then it's said to be disconnected. Really? Yeah. It's rocket science. Okay. So an example of that would be, say I have the same graph, but in this case, well, it's almost the same. Didn't quite draw it the same, but you know what I mean. Notice that there's a point sitting off by itself. That's disconnected. Or what if I did it this way? Those are both disconnected, right? Yeah. From each other? All right. So those are examples of disconnectedness. Non-essential characteristics may have a vertex without an edge. Or may have more than one component not connected. And I'll talk about components in a minute here. So here's another example of a disconnected graph. Notice that O is sitting by itself. It has no edge to it. So they're made up of pieces that are by themselves connected. Each piece is called a component. So when these three are connected to each other, it's a component of the graph, right? Okay. A bridge is an edge that, if removed from a connected graph, would leave behind a disconnected graph. So yeah, if I took off this right here, then I'd have two components, right? They're not connected anymore. What's another one that I could have removed to make it disconnected? X and Z, exactly. So Z would have been a vertex sitting out there floating by itself. So it would not have been connected anymore. So this graph is pretty easy to look at to see that, but if you look at the one on the left, it's not quite so obvious. What component, what edge could I remove to make it a disconnected? Yeah, F, if I took that off, R would be by itself, right? How about another one? GL, okay? Those two edges, if I removed, they'd leave it an open vertex sitting there. But if you were to look at the other edges on the graph, there's not any one that you could remove that would make it disconnected, because they already have another edge coming from it. All right? So that is pretty much the end of section 1 in chapter 15, and your assignment for today is this. Okay?